First, I will introduce the general context of AI for science, and then I will make a focus on a specific problem, which is the modeling of dynamics for physical phenomena with pure data-driven methods. Okay? And modeling physics dynamics is a central problem with application in many domains, but when dealing with data-driven methods, this raises several challenges in terms of machine learning, and then I will focus on one central challenge, which concerns the generalization to multiple physical contexts. So said otherwise, machine learning or neural networks generalize on the distributions I've learned through the training data set, okay? And there are difficulties to generalize out of this distribution. And when dealing with physics, most of the time we are in out of distribution situations. So, so this is still a challenge with for applying machine learning to physics. And okay, and I will start on that. Okay, so let me start with the general introduction to AI for science. So this is a recent trend. Okay. Not so recent, but in its model form, it's quite recent. So it just emerged a few years ago, and things started quite slowly around 2018. But after that, it rapidly gained momentum, and now it has become a major topic. Okay? So more or less everybody is well aware of this central topic. Okay. And it's now considered as a new scientific paradigm, okay? And this changes a lot of things, okay? This changes the way we can do research, okay? The type of questions we can ask, both for research and engineering, and it also considerably accelerates the development in some scientific domains, okay? So we are still at the beginning of this process, okay, but it's really gaining a lot of popularity. Okay, so now what I will do is that I will rapidly go through some recent success stories for AI for science. Okay, and I will start with applications for weather forecast. So a few years ago. I think it was, yes, in 2022, we have seen the emergence of machine learning models for weather forecast. Okay, those models were trained on data provided by the European Center on Medium Range Weather Forecast. Okay, so it's a huge data set. It's a simulated data set. It's what you call a reanalysis data set, which consists of 40 years of reanalysis of early reanalysis data. Okay, so we have foreseen the emergence of several models for several machine learning models for weather forecasts, and as you can see here, most of them were proposed by GAFAs or by the Chinese bats companies. Okay, and here on the right you have one of those models that have been developed. So it's called Atrass, has been developed by Microsoft. Okay, and so it's one of the last models that has been developed on this topic. And technically, this Aurora model leverages recent developments on transformers that have been mainly proposed in the vision community. Okay, and this type of system now is operational. Okay, so this means that the performance are on par with classical simulation models. The main difference is that they are much faster. So here are some figures. So IFS numerical simulation is a classical simulator by ECMWF. Okay, so typically for running a 10 days forecast, it takes about 1 hour on a large CPU resources. Okay. For this model, for Aurora, once it has been trained, so it takes a while for the training. So you can see here something like in between 2 and 3 weeks on GPUs. Okay, but once it has been trained, it can perform inference in less than 1 minute on a single GPU unit. Okay, so this means that it's a considerable speed up compared to traditional simulation models. Okay, and here are some examples. So the European Center is hosting different models. Okay, that operate online and on real time. So here are some examples. Okay. And so you can see here on the top, you have examples of predictions by the Aurora model. So if you go to their site or to the site of ECMWF, okay, you can see those models operating predictions and different forecasts in real time on a future window of 10 to 15 days. Okay, and the ECMWF recently developed their own models, okay, which is called the AIFS, okay, and this model is operational since February this year, 2025. So you can go to their site and see the many real-time predictions that the model offers. Okay, so this is probably one of the most successful development over the last years of machine learning for physics. Okay, here this is it's a second domain. Okay, a second domain with high stakes, which is drill design. Okay, so the objective here is to develop compounds that can bind to specific pathogenic protein targets. Okay, here the machine learning model is a classical language model, so it's a GPT-like model. This model is trained as for a language model on sequences. Okay, so typically here the model operates on string representation of molecules, so it can be trained as GPT on the prediction of the next component of a molecule or the next molecule. Okay, because it's self-supervised, it can be pre-trained on very large corpora. And here for this specific example, so it's a specific example. This specific example targets inhibitor compounds against tuberculosis. Okay, and this is how the model is used. They have been developing what they call design, refine, and test pipelines. Okay, so this means that they proceed in the following way. Okay, they use machine learning to generate several candidate compounds. Okay, and then they use traditional methods in order to filter and to select some of the generated compounds. Okay, so usually what they do is they generate a few compounds, and then they iterate this process. And so they repeat the process until they select a few compounds for in vivo experiments. So the idea is that it considerably accelerates the process compared to traditional methods. Okay, and my last example will be for the reasoning abilities of machine learning. So my example here comes from reasoning in math. Okay, so again, this is something that started a few years ago. So people have started to train. Once again, here it's models very similar to large language models used for ChatGPT and all this type of models. So they started to train them on large collections of mathematical problems. So here, for example, you have the description of the data set. This is called the math benchmark, okay? And so you have about 10,000 problems, mathematical problems from high school. So you have the description of the problem, then you have the description of the solution, the reasoning, okay? And then you have the solution. And they train models, they train LLM models from scratch on this type of data. This type of data is just text. Okay, so you can train them as we do usually with LLMs. Okay. So at first, so you can see on the right, on the top right here, the performance of the model were really bad. Okay, so here it's a measure of performance. Okay, so let's say it's the accuracy, the ability of the model to discover the solution. Okay, the final solution, let's say. So you can see that the performance are really bad, something around 5-6% of success rates. But within a few years, okay, people were able more or less to solve the problem. So now, on the bottom of the on the right bottom of the figure, okay, you can see the current performance of the state-of-the-art models, and the success rate is about 95%. So more or less the problem is solved. Okay. So after that, people started to work on more complex reasoning models. So here are there are several instances of these models, but here I took this example of the alpha proof models, which has been deployed for solving mathematical problem for the math Olympiad. Okay. So here the model is much more complex and much more sophisticated. So target here is that the target has a problems that are for the Olympiad. So they are both they cover different areas, both from algebra up to number theory. Okay. The models are, as I mentioned, more complex. They combine the large language models with some form of reinforcement learning algorithm plus some formalism for formal proofs. Okay. But anyway, okay, they developed the system, and last year they were able to reach the level of what they call a silver medal, which means that they were able to solve a given ratio of problems submitted to the Olympiad. And this year, in 2025, they reached the gold medal level. Okay. Well, so that's it for the general introduction. Okay, now I will turn on a specific problem, okay, which is within this general context of AI for science, and this is a specific problem of modeling physical dynamics with machine learning. So I will focus on what we call pure data-driven approaches, okay, which means that my models which just try to exploit the knowledge which is in the data, okay, without any prior knowledge.
But Patrick, since you are now moving to after the introduction, there has been one question on the chat, which maybe you can answer now. And although it is very general, but you are going to be more specific now. It's a question by Laurent Gasser, who says, in previous science, the knowledge was expressed as laws of nature. What are the new forms of knowledge?
Okay, the new form of knowledge is data. Okay, and so it's a very short answer. But okay, what I'm trying to introduce is the fact that we have both complementary and an alternative paradigm to the classical way. I mean, classical way is what we learn at school, all of us. Okay. So the classical way, which has been developed in physics and in many domains, is that well, you first try to gather a lot of knowledge about a given domain or a specific phenomenon, okay, within this domain, and then once you have worked a lot on this on your problem, you formalize it using, for example, equations, but also formalisms as well. Okay, and then okay, you may use some computer resources to try to solve the problem.
Laurent Gasser, are you? Sorry, I don't want to interrupt. Sorry.
No.
Laurent Gasser, are you satisfied with his answer?
Yes.
No, but we could have a discussion on that. But
okay,
let's go. In my talk, I purposefully take the point of view of pure data-driven methods, okay, there are a lot of things in about on the topic of combining data-driven methods with the more traditional way of developing solutions for science. But this is not my topic today.
Okay, let's continue.
Mm-hmm. Well, okay. Well, so basically, I consider that the only information is in the data, and of course, this makes the assumption that you have a lot of data, so that you are able to at least extract some part of the knowledge you want to extract. Okay, so I do not claim that one solution is better than the other. Okay, but in my opinion, it's really complementary. But okay, well, so I go in this okay for my second topic, which is the modeling of physical phenomena. I will focus, as I mentioned, on pure data-driven approaches. Okay. Well, so as I indicated, the modeling of physical dynamics, it's really a fundamental problem in science with many applications in many domains. So here I have a few illustrations. Okay, for example, on the left, on the computational fluid dynamics, both for just predicting the dynamics or for design of sophisticated objects like cars. Okay, you have a lot of applications in aeronautics too, and so on. Okay, you have applications I already mentioned in for climate and weather predictions, and also for graphical design. Okay, so the objective here is to use machine learning to provide alternatives to numerical solvers. Okay, so one of the maybe most popular objective is to develop models that are able more or less to produce the performance of classical models used in fluid dynamics, for example, at a reduced computational cost. Okay. Another objective is the development of hybrid models when you combine both. So you try to exploit the strengths of both approaches, and maybe in the future, at least for some domains, for some application, we'll be able to use pure data-driven approaches in order to replace solvers for specific applications. Okay, so just to mention that it's an important application domain for machine learning. Okay, so the traditional way is, well, as we already discussed, to develop an explicit modeling of the problem you want to deal with. Okay. So typically, well, you are a specialist of a problem, and you will have an explicit formulation of your problem. So here it's just for modeling dynamics. So it's classical formulation here. Classical mathematical formulation is through partial differential equations, and so this partial differential equation will well summarize your background or your knowledge on the evolution on the dynamic evolution of physical model. Okay. For now, if I consider pure data-driven approaches, I do not have any information or any prior information about the phenomenon. Okay, and my only information comes from the data, and this is what I call implicit modeling. So I want to exploit the data here, plus general mechanisms encoded in machine learning models in order to extract information and to develop surrogate models for my problems here for modeling dynamics. Okay. Well, so when we try to do that, we face several challenges. Okay, and here I have listed a few of those challenges. So one is physical consistency. So very often, what we get. So you know that machine learning models are trained to optimize some loss function, and this loss function does not always perfectly reflect the physics underlying your phenomenon. Okay, so most often you get good performance according to this loss function, but the model you obtain is not physically consistent. Well, and physicists and okay, anybody in different domains, in a different scientific domain, want models that are consistent with here with the physics or with the chemistry, the biology, or whatever. Okay. Well, so this is one of the current challenges. Another challenge is the one I will develop later on, is generation and extrapolation. So typically, when you train machine learning models, they perform well on the distributions of the examples you have provided for training, but they have difficulties to generalize outside. And this is much more sensible for applications in scientific domains like physics than with classical application domains of machine learning, like dealing with semantic data, okay, like text, images, and so on. Okay. Another problem here, another challenge is exploitation of data scarcity and heterogeneity. So this is a classical problem in engineering. But okay, we have specific problems with machine learning. And then here, my last 2 points here are the development of hybrid systems that try to exploit both physical prior background and the information that you can extract from data. Okay, and then there is computational efficiency. For example, for modeling dynamics, okay, most of the academic developments perform well on toy problems or on small problems, but we are still far from scaling to real world problems. Okay. So here in color, you have the different problems we have been working on in my group, and I will develop the generation problem in red. Okay. So what's the problem of generalization? So once again, okay, when you have physical models, they are developed from first principle, okay, and they rely on our human understanding of the phenomenon. And usually, when you formulate laws, well, they are correct or at least approximately correct, and they capture some form of causality, okay, between the different variables of your problem. And doing so, you know what is the domain where your model is correct, and what also context where your model is not correct. Okay, when you are using pure data-driven methods, okay, you learn from data. You do not have prior knowledge, okay, and your model will only capture correlation between the features of the data. Okay, and you know that very often this correlation can be spurious. Okay, which means that most often you do not capture real causality. Okay, or the real underlying physics, okay, behind the phenomenon. Okay, and if you are not able to capture this causality, you will not generalize outside the training distribution. Okay, well, so this is what I mentioned. So people in machine learning have tried to solve this problem as they do usually. Okay, typically by using what we call empirical risk minimization, which means that you try to gather more. This is exactly what they have been doing, for example, for successful applications for dealing with semantic data like text or image or vision in general. Okay. Well, so what people try to do is to gather more data, which is not so easy for when we deal with physical problems. For example, simulating data is quite complex and costs a lot, okay, computationally. Okay. And well, and so what they try to do is to learn on more data and hope that this will provide generation. But this does not work usually, especially of course in context where you only have a few data available, and also because the complexity of physical phenomena is often order of magnitudes higher than what people have been dealing with in machine learning, even for complex applications like, for example, GPT models or whatever. Okay. So here I will introduce two challenges we have been working on. Okay, concerning this generalization. So here on the left we have my explicit modeling with partial differential equations. Okay, so this says partial differential equations are defined on specific domains. Okay, and then when you use when you perform simulations, your simulators will leverage some form of discretization of spatial and temporal discretization. So if we consider only spatial discretization, for example, your simulator will work on predefined grids. Okay, so these grids could be regular, like for example in a weather forecast, or irregular, like what people are developing in most applications in fluid dynamics for design, for example. Well, okay, so we want our neural models to generalize on different domains and on different discretization. So typically, what we do is that we will train your model, the model on different data. As the data have been collected on different domains with different discretization, and we want to be able to generalize to domains that are not so far from the ones the model has been trained on, but that are different. Okay, and the same for the discretization. Okay. And the second problem here is generalization to different phenomena that more or less follow the same dynamics, but different instances of the dynamics the model has been trained on. So typically here, when you have on the left, when you have partial differential equations, this partial differential equation will depend on different parameters, like for example forcing terms, coefficients, or or whatever. Okay, and when you train a model, okay, your model will be trained on specific instances of this equation or of the physical phenomenon, and you want to be able to exploit it on different instances. I mean, instances that could correspond to other values for example, for the coefficients of the forcing terms and so on. Okay, so this is another generalization problem. And well, in machine learning are pretty bad at doing that. Okay, well, so I will first introduce the solution we have developed for the first problem. And this solution belongs to a topic that has been developed since a few years. This is the topic of neural operators. So I won't be technical in my descriptions. Okay, I will just try to introduce the main ideas. Okay, so here I present a solution for dealing with generalization in the discretization and domains of the physics. Okay. So the classical solvers operate on grids and meshes. Okay, so here you have examples. So design example here in aeronautics, and the example below is for an example in weather forecast. Okay, and the first neural solvers that have been developed try to mimic exactly what the classical solvers were doing. So they were operating on grids or meshes, which means for machine learning or deep learning, operating on matrices or tensors or graphs. Okay. And a few years ago, people started to develop what is called now neural operators. Okay. And the objective of neural operators is to learn mapping between function spaces instead of learning mapping between vector spaces. Okay. So typically here, if we consider that the grids here and the values of these grids are images, okay, the images are considered as continuous functions, and you want to learn mappings between two continuous functions, so one input continuous function, the one on the left, for example, here, and another continuous function, which is the one on the right, okay, which would correspond to the state of the dynamics. Okay, and the potential benefits are that this type of operator is supposed to be mesh and resolution invariant. Okay, it is supposed to be able to handle different geometries and multiple resolutions, and you are supposed to be able to query your model at any space-time coordinate. Okay, so this is a potential benefit, but it's not okay. So the early models that have been developed for neural operators were not so able to reach all those benefits and to exploit all those properties. Okay, so I will introduce a framework. Okay, we have developed quite recently, which performs quite well. Okay, so this framework is able to more or less to meet all these expectations. So it is able to handle different geometries. Okay, so for example, the input and outputs of your model could consist in different geometries like point sets, grid, or irregular meshes. It can be created at any spatial position. Okay, and my message here is that this is a specific model. There are many models that are more or less similar to this one that has been proposed recently. But the key idea here is that this model exploits modern neural network components. Okay, and there's recent neural net components are quite efficient to provide solutions for modeling complex problems, like here modeling complex dynamics. Okay, so the general framework is now known as encode process decode, which simply means that instead of operating in the state space, in the physical state space, okay, because we want models that are able to scale, okay, to large size dimensional problem. Okay, what we do is that we first encode the physics into a latent space in order to then to be able to proceed in a more compact and smaller dimensional latent space. Then within this latent space, we learn a model of the dynamics. Okay, and once the model has been learned, it is able to perform time stepping, for example, say, well, like performing forecasts, okay, for future forecasts, okay. And then once the forecast has been performed, you can go back through a decoder to the physical space. Okay, so this is general framework that is created now by different models. Okay, so that's it. And this is a general organization of the model. So you have an encoder here. So I don't go into the details, but this encoder here relies on a mechanism which is called cross-attention, and this is one of the mechanisms that is exploited in large language models, okay, or in vision transformers, okay. And the benefits of this cross-attention is that it can take as input, for example, point sets, okay, a variable number of point sets or points on a grid, okay, on a regular or an irregular grid, okay, and it will be able to map a given number of point sets onto a fixed size dimensional latent space. Okay, so you can take, for example, you want to exploit data from a given number of sensors. Okay, so you'll be able to project your physical observations onto fixed size dimensional physical state. Okay, then you consider another set of sensors. You will be able to map the data coming from this different set of sensors onto exactly the same dimensional space, same dimensional latent space. Okay, so this is the idea. Okay, and then once, okay, and here this is just to illustrate that this latent space here is able to capture local spatial information into the original physical space. So you have a latent space, and the latent space is able to capture relevant information, in this case, local physical information characterizing your phenomenon. Okay, and then once you have a projection on a latent space, you will use a model. Here it's called something which is called a diffusion transformer, which combines a transformer with a diffusion model. Diffusion models are stochastic models. Okay, so you have a form of stochastic generative models relying on transformers for performing time stepping. So, for example, for doing a forecast in the latent space, and then once you have performed your forecast, you can go back through a decoder the physical space, okay, and get your results here. Okay, so I will skip this one. Okay, this is just to show some examples, some simple examples that we have been able to visualize with this model. So this is something which is called Burger's equation. So here the different colors correspond to the time and the x-axis corresponds to the space. Okay, so it's a one-dimensional equation here. And the time unfolds from the blue line on the back up to the red line on the top. And here, for example, this model has been trained on 50 time steps. And here you can see enrolling on 200 time steps. So it's a forecast application. Okay, so it's just to say that, well, at least in some simple models, this simple problem, this kind of model is able to perform quite well. Okay, and also, wait, this is just to illustrate that the model, because it incorporates a stochastic component, it could be used for performing some form of uncertainty quantification on the simulations. So you can see here different rollouts of the models, and just let's have a look at to the graphic on the right side here. You can see that here you have 100 rollouts of the model, and because this is an autoregressive model, the error through autoregression accumulate, and you can see here that you have an evaluation of the uncertainty of the model. Okay. So that's it. Okay, well, so this is for my first generation problem. Now I will focus on the problem of solving parametric PDEs. So again,
maybe in less than 10 minutes, Patrick.
Yeah, sure. I'll skip if it takes too much time. Okay. Well, so what is this generation problem? So here you have different examples. So let's for example consider the central figure here. So this is was a prediction problem where the problem is to predict the sea surface temperature, okay, on the ocean. Okay, so typically if we use machine learning, what we will do is that we will divide here the physical space, the ocean here, into small patches, okay, and we will train a machine learning model on two subsets of these patches, okay. And the objective is that once it has been trained, the model should be able to generalize to other physical regions, okay, also physical regions or spatio-temporal regions, for example, like other seasons on the ocean, okay, and so on. Okay. So what it means is that for each of these local patches, okay, the underlying phenomenon is the same. It's fluid dynamics, okay, so it can be modeled by a fluid equation, okay. But on for example, on the different locations, this corresponds to different parametric forms of the equation, okay. So the interactions with, for example, with the atmosphere, okay, so the forcing terms could be different. The coefficients of your equations would be different, and so on. Okay. So the idea is that you learn on a kind of specific instances of parametric equations, and you want to generalize to other instances, and this does not work very well. And you have other examples here. On the right, you have okay, something that corresponds to the modeling of electrophysiology, okay, on the Earth, okay. So the objective here is to model the electric activity of the electric cardiac activity. And for different people, you have different, once again, it's exactly the same story. You have the same underlying equation, but at different position in the, okay, on the Earth here, you have different instances of the equation. So you will train your model on specific instances, but it will not be so easy to generalize to other instances. And on the left, you have exactly the same story, but here is just the modeling of epidemics in different countries. So this is here, this is COVID, but according to the different well, socioeconomic and local context, you will have different dynamics. And once again, it's exactly the same equation or the same phenomenon. Okay. So the idea is that when you train a model, it does not generate well outside of the training distribution. Okay. Well, so the idea we have developed is the following. Okay. We make the assumption that the data come from different domains, okay, and we keep track of this domain. So what people usually do in machine learning is that you collect data from different contexts, different domains, and then you shuffle everything, and you just forget the origin of the data. Okay. Oh, here we keep track of this origin. The assumption is that all the domains share the same forms of dynamics, but one domain will correspond to a specific form of the dynamic. Okay, and the problem is to train pure data-driven models so that they are able to extrapolate to out of distribution data, or I mean to all the instances of the same dynamics. And the claim here is that if we proceed as we do usually in machine learning, this will not work. Okay, and in order to be able to generalize, we must condition the model on the characteristics of each environment. So this is the idea. So I will skip this one. So I will briefly introduce in 5 minutes 2 ideas. Okay, that develop 2 frameworks. Okay, two recent frameworks that have been exploited in machine learning for large models. One is based on classical optimization strategies, okay, which means that you will condition a model on a specific context, and then you will adapt your model through classical optimization strategies performed through, for example, gradient descent here. Okay, so this is the first idea. Okay, so I just present the intuition. So the intuition, we want to train models, okay, and so that these models are able to operate on different environments. So we have a set of training environments, and we want to train them in order to be able to generalize to new environment. So this is called meta learning. We want to train model in order to be able to generalize. Okay, so we train them to be able to generalize to. Okay, so we have a kind of double loop for training here. Okay, so this is the general idea. Your model, we have parameters here, for example, like theta here, okay, and theta e. The parameters of a specific model specific for an environment, will be composed of parameters shared by the different environment plus parameters that are specific to a given environment. And what you want to do is that when you face a new environment, okay, you want to train your model to be able to adapt fast from the shared parameters to the parameters that are specific to this environment. Okay, and this should be you should be able to do that very fast and using only a very few amount of data characterizing these 2 environments. Okay, and this is just an example of this strategy. So here it's just a simple example for illustration. So you have here it's not even a PDE, it's an ordinary differential equation. So it's called pre-predator model. So you have 2 species here, prey and predators. So the predators hit the prey. Okay, so you start with a given number of prey and predators. The predators eat the prey. So okay, so at first the population of predators increases. Then when there are no more prey, there is nothing to eat, and the population of predators decreases, which means that the population of prey starts again increasing, and so on. Okay, so here you have 2 parameters governing these equations. Okay, and here we have trained the model on a sample, on a small number of samples, which correspond to this to the yellow dots here. So this corresponds to a small number 9 here example 9 samples of the dynamics. Okay, and here the objective is to generate to other dynamics, and this is what this figure illustrates. So I won't go into the details, but what the figure illustrates is that the model is able to generalize on the blue domains of the parameters, which means that it is able to generalize, to extrapolate outside the domain on which it has been trained. So this is just the general idea, okay? And now I present such a second idea, okay? And the second idea exploits something that has been recently used for large language models, which is called in-context learning or in-context training. So the idea is the following, okay? With large language models, so you are used to ChatGPT and similar models, okay? So you know that these models have been trained on very large corpora, and that they have been trained on different tasks, okay? But then they can be queried on new tasks. For example, here, suppose you have a model that has been trained, and this model has been trained on different corpora, okay? But this model has not been trained for translation, okay? And you can query this model to perform translation tasks just by providing the model with some examples. So here, this is called few-shot learning. So here you provide them with some examples for translating from English to French. So you have examples of translation, like for example, sea otter and l'outre de mer, and so on. Okay, so the model is supposed to have seen all these different items of the different words in the training set, but it has not been trained specifically for translation. Okay, but it is able to do so. And this model is able to do that without any optimization. So this is much cheaper than doing optimization and adapting the models through optimization strategies. So this is the general idea. So I will skip that. And I just want to highlight here that we can use exactly the same strategy for training models to learn dynamics. Okay, so here I will just use exactly the same thing. So I will train model, okay, in order to perform, for example, here forecast tasks, okay. And once the model has been trained, I want the model to be able to adapt to a new dynamics just by providing him with an example of this dynamic. Okay, so suppose the model has been trained, okay, so it has been trained again to be able to generalize to new dynamics. And once it has been trained, I provide him with an example of a new dynamic, and then I give him an initial condition, okay, which does not correspond to this to the context example I just provided in. It's another initial condition, and I want the model to be able to infer the dynamics, okay, corresponding to the context, but from this new initial condition. So I'm not sure I'm very clear, but okay, I give it an example of dynamics, and I want the model to infer the dynamics starting from a new initial condition. Okay, so that's the idea. Okay, and for that I will use a model which is directly inspired by the models that people have been developing for large language models. So it's a discrete transformer. Okay, so you have the main component here is a transform. Okay, it's an autorecursive transformer, and we can use this model to generate to model the dynamics of spatiotemporal dynamics in physics. Okay, so this is an example of how it works. Okay, so for two simple equations, two one-dimensional equations here. On the left, you have a heat equation, which is okay, a very classical equation. You have on the top left a context prompt. So this illustrates the dynamics. So once again, here it's a one-dimensional equation. This is the space. The space dimension here is on the x-axis, and the different colors here corresponds to the time dynamics. Okay. Okay, so you start from the blue lines here, and you end up with the red lines. Okay, so this is a context dynamics. You provide the model with an initial condition, and it is able to develop exactly the same dynamics, but starting from this initial condition. So this is the prediction, this is the ground truth, and this is the same thing here for another equation. Okay, here you have exactly the same thing with a two-dimensional example. Okay. And well, I will skip that and I will stop here. Okay. Thank you. Thank you for your attention.
Very quick conclusion, Patrick.
Yeah,
Thank you
yeah,
very
sure,
much.
but okay.
Thank you very much. It was very impressive, full of impressive results. And also, I appreciate that you underline the fact that we are celebrating this year the 100th anniversary of the Lotka-Volterra equation.
Well, it was not on purpose, but
which I used to teach in system dynamics many years ago. I have not seen comments on the conversation. I don't see any hand raised, but we have time for a few questions. So since no one is raising hand, then I will ask first question, because here we are talking about trustworthy AI. That's the main topic of the subject, and also risk assessment for AI. I assume that people will make decisions based on the surrogate models that are built using these technologies. And so, and the results are very convincing. I mean, you show the ground truth and the results, and they are very, very similar. But apart from this empirical impression, is there any way to guarantee the result of the neural network?
No. Here we have no model. We have no formal model, and we have no guarantee. The only guarantees are it's exactly the same thing as for LLMs. Okay, so all the problems of hallucinations and all that. Okay, and we hallucinate exactly the same way. Okay, so the only guarantee is that you have been able to train your model using either a lot of data. Okay, or by adding prior knowledge. Okay, so I didn't talk at all about that, but you can incorporate constraints to your model that force the model to respect some form of some properties of some physical properties. Okay, typically, but we have no guarantees. We have no formal guarantees at all. Okay?
So I assume that some users in critical domains will be reluctant to use this without guarantees.
That's true. But it has been exactly the same thing for a long time in machine learning. Okay, and okay, I must say that very often, okay, you have guarantees, but even with formal models, but those guarantees in practice are pretty weak. Okay, it's just that they do exist. Okay, when you have guarantees about the stability of a model and so it works for example for linear model, but when you want to go beyond. Okay, even if you can have some formal results, okay, it's not really a guarantee.
Okay. I see Martin. Martin typed questions in the chat, but maybe you, Martin, you can ask your questions.
Yes. Can you hear me?
Yes.
Yeah.
Okay. Thank you. Thank you very much for your talk. I have 2 questions. I'm just gonna read them since I just put them in the chat. What kind of conditioning do you provide? This is for the first part of the talk, like first experiment. What kind of conditioning do you provide for the sampling with the diffusion transformer in the latent space in such a way that you maintain physical constraints? With this question also comes the nature of these constraints, like are they soft constraints, hard constraints? My guess is that they are soft since stochasticity brings some complexity. And the second question is, have you tried flow matching approaches to try to impose harder constraints precisely via this very explicit diffeomorphism formalization that they provide, and that even if they are equivalent in some sense to these fusion models, the flow matching approach thanks to this diffeomorphism formalization, manages somehow to impose these hard constraints.
Yeah. Okay. So in the example here, so I just mentioned pure data-driven approaches, so without any prior physical constraints. Okay. But you can do that. Okay, of course, and okay, so what we did is that in the past is that we combined this type of approach, as machine learning approaches, with prior knowledge. Okay, and typically we try to combine machine learning with differentiable solvers. Okay, and this allows to to impose constraints. Okay. How could we do that? So here it was just our objective was just to generate, to learn distribution of trajectories, okay, and using this distribution to be able to provide some form of quantification of the both epistemologic and aleatoric uncertainty of the model. Okay, and in this sense, this provides some form of let's say guarantee. Okay, at least we know when the model is not in its comfort zone. Okay, so I don't know if I precisely answer to your question. And then, so we did that with diffusion model in this example. But right now, and mainly because diffusion models are quite heavy, okay, we try to exploit flow matching, and so flow matching is easier to control, but we did not attempt to impose external or prior constraints up to now. Okay. Mm-hmm.